Hey everyone, welcome back. So in this video, we shall study difference equations. So these difference equations will give us a tool for solving different kinds of equations that keep routinely popping up in time series specifically. So this is a useful tool to have in hand, especially because we will be solving a lot of equations. So we will start with difference equation of order 1. So if you have a sequence of numbers u0, u1 and so on that satisfy this particular equation, this is equation 1. So this is a homogeneous difference equation of order 1. So I'll quickly show you an example of when this form pops up. So if xt is autoregressive one process, if you go back and look at the autocorrelation function of AR1, you will see that it satisfies this particular equation. Okay, so this is rho h is like the un, and rho h minus 1 is like this un minus 1. So in the autocorrelation function, so far we've been using different techniques and different methods to obtain autocorrelation function. But here, if we knew how to solve this kind of equation, we can use that same technique to obtain the autocorrelation functions here. So how do we solve these difference equations? So if you plug in n is equal to 1, you get this. You plug in n is equal to 2, you get u2 is equal to alpha u1, but we know what u1 looks like, so plug in, we get alpha squared u0, and you keep continuing this way, and ultimately you'll find that un is alpha times un minus 1, which is, so you can plug in the value of un minus 1 and you'll find this. So it is alpha raised to n times u0. So for difference equations of order 1, un is alpha raised to n times u0. But we don't know what u0 is. So u0 can be calculated from an initial condition. Okay, so in initial condition, we know that rho of 0, right, that is correlation at lag 0 is 1. So in that case, our u0 would be 1, right? But that's just the AR1 case. But in general, we can always, so we can we have these initial conditions where we can specify what u0 is going to be. And suppose u0 is c. If u0 is c, then un is going to be alpha raised to n times c, right? So this u0 is the is equal to c. This is the initial condition. It's something that we specify from some other information that we have at hand. So in the operator form, this un minus alpha un minus 1 can be, written in this particular fashion using the backshift operator. The polynomial associated with this or this operator is alpha z, so it's 1 minus alpha z, right? N minus 1, so it's z. If I had n minus 2, I would write z squared, right? So the polynomial associated with this is 1 minus alpha z. And if you think about the root of this polynomial, right, it is which I'm going to call as z0. So z0 is the root of this polynomial. So it's 1 by alpha. So the solution to equation 1, so equation 1 is the difference equations of order 1, right? So solution to the equations along with the initial condition has this form. So in the previous slide, we know that un is alpha to the n times c, where c was the initial condition. But what is alpha, right? We need to figure that out as well. So once we figure out what alpha is, then we have this complete then we can actually calculate un, that is, we have the complete solution. So I'm telling you that this is the solution for this equation 1, and we'll check that this is a solution very shortly. But note that so the solution to this difference equation, right, this is a solution. It depends on this initial condition c, and it depends on the root of the polynomial. So again, we'll find that in difference equations, even the more general ones, to solve for them, we will need initial conditions and we will need these roots of these associated polynomials. Okay, now to verify that the solution that I mentioned is in fact the solution. So this is what I said, un is equal to this is the solution. So if you want to verify if it's a solution, what do we do? So I'm saying that this solves this equation. So I'm going to plug in these values in this equation and see if we get 0. Okay, so in place of un, we'll plug in z naught raised to minus 1 raised to n times c. In place of un minus 1, we'll plug in z naught raised to minus 1 n minus 1 times c, right? So we are plugging in. So we plug in here, simplify, rearrange, and you'll find that it gives you, ultimately you end up with a 0. So which means that this is a solution to the first order difference equation. So now let's take a look at difference equation of order 2. So in yellow here, this is the equation of order 2. So you can see that you start from un and you go back to 2 steps. So your last term is alpha 2 un minus 2. Then alpha 2 is non-zero and n starts from 2 onwards. Okay. So the associated polynomial with this is going to be 1 minus alpha 1 times z1 minus alpha 2 times z square. And this is a quadratic. It has 2 roots, right? Say those 2 roots are called as alpha, z1 and z2. So if z1 is the root, then we know that alpha of z1 is going to be 0, right? That's the definition of the root. And if z2 is the root, then alpha of z2 is also 0, right? So these are the 2 roots. Now there are 2 possible cases that these 2 roots, that z1 and z2, are either equal or they're not equal, right? So suppose they're not equal to each other, that is, the roots are distinct. Then I'm telling you, so I'm giving you the formula here, that the general solution to this has this particular form. So un is going to be c1 times z1 raised to minus n plus c2 times z2 raised to minus n. Again, we can see that, so c1 and c2 depend on initial conditions. And z1 and z2 are roots of the polynomial. So again here, the general solution depends on the initial conditions and the root of the polynomial. Again, we will go ahead and verify that this is in fact the solution of this second, of this equation 2. So this is the difference equation. This is the solution. So what I'm going to do is I'm going to plug in this into un and we are going to verify if we end up with a 0. So this is un, and then for alpha 1 times un minus 1, you plug in n minus 1. Then alpha 2 times you plug in the n minus 2. And then you rearrange the terms. Okay, so you'll see that, so rearrange the terms, further simplify them. So look at this. So we have this 1 minus alpha 1 z1 minus alpha 2 z1 squared. This is the polynomial, right? This is the associated polynomial. And the same thing here. This is also the associated polynomial. So I can replace this with alpha times z1, right? Because alpha times z1 is exactly this guy. And we know that z1 and z2 are the roots of the polynomial. Therefore, these are 0. And therefore, we end up finally with a 0. So we have verified that this formula here of un, that this is the solution of this particular, of this difference equation of order 2. So this is just for case 1, right? Here we assume that the 2 roots are distinct. But before that, so So this is the solution, but we don't know what C1 and C2 are yet, right? So we have this general form, but we don't know actually what to plug in here. So basically we'll see how to determine C1 and C2. So again, we will use initial conditions, and I'll show you exactly how to use initial conditions. So suppose we know somehow that U0 so U0 is C1 plus C2, and suppose and so if we have this, so U1 is so you plug in 1, right? It's C1 plus C2, okay? So U0 and U1 are these values that I know from initial, the values that I just know. So in the AR1 example that we saw previously in this video, U0 was equal to 1, right? So somehow I know what the value for U0 is and the value for U1 is. So these two are known. So I'm trying to determine C1 and C2. And in these two equations, my knowns are only U0 and U1 so far. So we need to figure out Z1 and Z2 as well. Okay, so how do we determine Z1 and Z2, right? So remember that these are roots for this polynomial, okay? And so we can use the quadratic formula. Right? So yes, so we use a quadratic formula, and if this is just a general formula that I'm stating here just for review. So if you have equation ax squared plus bx plus c, then it has two roots. First root is minus b plus b squared minus 4ac by 2a, and this is the second root, right? So to solve for this, we can use the same quadratic formula. So Z1, so now we know that Z1 has this form and Z2 has this form, okay? So going back to our equations, so we have this U0 is C1 plus C2. We still need to find out C1 plus C2. But now we know what Z1 and Z2 are, right? So alpha 1 and alpha 2 are known, and therefore Z1 and Z2 are known. We can calculate these numbers. Once we have these numbers, we can plug into these equations, and then we know U0, we know U1, we know Z1 inverse, Z2 inverse, and now we can solve these to find out C1 and C2. Okay, so with this we know exactly what the general formula for this, so we know exactly what this solution to this difference equation of order 2 is. So we have determined all the different components of this solution. So things will be a little bit more clear once you work with an actual example, but it's important you understand the basic principles and this formula basically. So now we go to the second case where the two roots are the same, that is Z1 and Z2 is the same, and we just call this value as Z0. So this is the case of common roots. So if this is the case, then the general solution to 2 has this form. So I'm giving you that this is the formula. If Z1 and Z2 are the same, then this is how the solution of this equation looks like. Now it's slightly more complicated to verify that this satisfies this particular equation, so we won't get into it. So just to summarize, okay, so this is the homogeneous difference equation of order 2. This is the associated polynomials. It has two roots, Z1 and Z2. We have case 1 where Z1 and Z2 are distinct. In that case, this is how the root looked like, right? So remember, alpha 1 and alpha 2 are known, and in this, to actually find out or to compute this root completely, we need to determine C1 and C2, and we used initial conditions to get what C1 and C2 look like. Also, we use a quadratic formula to find what Z1 and Z2 are, right? So we have all of these numbers basically, so we can actually find out what UN is. So case 2, the two roots are the same, and then the formula for the root is, or the solution is given as this. So we'll try to write this more generally, okay? So for case 1, the solution to the difference equation, that is this, I'm going to rewrite it. So it's Z1 times, right, polynomial in n of degree m minus 1. We'll come shortly to what this m1 is. And then Z2 raised to minus n, so you have this term here, times polynomial in n of degree m2 minus 1. So what is m1 and what is m2? So m1 is the multiplicity of z1 and m2 is the multiplicity of the root of the root z2. So just a quick recap of, or just a quick review of what multiplicity is. So if this is the equation you're solving, right, then we know that one root is minus 4 and the other root is plus 1. So minus 4 has multiplicity 1 because this root just occurs one time, and x minus 1 squared, so this root 1 occurs 2 times, right, because we have the square here, so this root 1 has multiplicity 2. So basically it's the number of times that root occurs, right, when you solve for the equation. And we were assuming here that z1 and z2 are distinct. So multiplicity of z1 is 1, that is m1 is 1, and m2 is also 1 in this case. So un would be z1 inverse polynomial in n of degree 0, which is just a constant, right? A polynomial of degree 0 is a constant, and same thing here. So we rewrote this in terms of z1 raised to minus n, and polynomials, instead of calling this a constant, I'm calling this a polynomial of degree 0, and I'm calling this also a polynomial of degree 0. Now to go to the other case, right, that is the two roots are the same. We can rewrite, right, so this can be rewritten as z0 raised to minus n times, so polynomial of degree m0 minus 1. m0 is again the multiplicity of the root z0, and remember we are saying that the two roots are the same. That means the multiplicity of z0 is 2, that is m0 is equal to 2. Therefore this un is z0 raised to minus n polynomial of in n of degree 1, right, which is exactly what you see here. This is a polynomial of degree 1. So we can generalize this format, right, to equations, to difference equations of higher order. So let's say we have a general or a homogeneous difference equation of order p. This is how the equation looks like. Of course, alpha p is 0, and now n goes from p onwards. The associated polynomial is given as this, right? So you have terms all the way up to alpha p raised to zp. Remember, z's can be complex here. And now things get a little bit more general. So this is an equation of order p. It's possible, so it has p roots, but it's possible some are distinct and some are not. So we are going to assume that this polynomial has r distinct roots. Okay, so r is going to be less than or equal to p. It has r distinct roots, and say z1 is the first root, which with multiplicity m1, z2 is another root with multiplicity m2, and so on. Then zr is the root with multiplicity r. And remember that when we sum all of the multiplicities, it has to be equal to p. So now the general solution for this can be written as z1 raised to minus n times p1n. So this is a polynomial in n z2 raised to minus m. This is also a polynomial in n. And see, I have p1, p2, and pr. That means all of these are different polynomials, right? So the pjn is a polynomial in n of degree mj minus 1. Okay, so this is a polynomial of degree m1 minus 1, m2 minus 2, and so on. So this is a general form. Of course, now to determine exactly what these polynomials, so these polynomials will involve constants, and what these constants look like, we will need initial conditions. And now that we are dealing with difference equation of order p, we need p initial conditions. So if you go back and think about it, in difference equation of order 1, we had one initial condition. For order 2, we had two initial conditions. So for order p in general, we need p initial conditions so that we can solve all of the equations and get this exact form of p1, p2, and so on till prn. So now we know how to solve a general difference equation of order p. So that's all for this video. In the next video, we should look at autocorrelation and partial autocorrelation. Both of these are important concepts. So there will be more examples. So I will be providing more examples about the difference equations in the assignment. So so once you solve actual examples, things will be a bit more clearer. So that's all for now. See you next time.